Hello, welcome back to this video 3-4 implicit differentiation from the essentials of calculus. In this video, we're going to cover more complex examples of implicitly differentiating. Just a reminder about the procedures. We're going to differentiate both sides with respect to x and use the chain rule, the hook-on factor for any terms involving y. And we'll have to collect those terms on one side, factor it out if possible, and we're definitely going to see that in the examples in this video, and then we'll have to divide that side for y prime. All right, so let's get to it. Here is example 3, and in example 3 we are given the equation x cubed minus 2xy plus y cubed equals 5x, and they want us to find dy dx and evaluate at the point 1, 2. So we'll go ahead and do just that. So we have 3x squared minus, and it's important to see here that we have x times y, okay? So that is the product rule. We're gonna have to go ahead and use the product rule. So I'm gonna put in a bracket here just to isolate these terms, okay? So we have the derivative, we have the first times the derivative of the second, so 2x times y prime, okay, plus the derivative of the first times the second, so 2y. All right, okay, so we just differentiated that term plus, okay, 3y squared, and that's the y term, so we have to take the y prime, okay, and then this is equal to 5. All right, so notice too here they say they want us to find dy dx. Again, I'm a fan of y prime, so those are exactly the same thing. So you can substitute in dy dx, feel free to, but I'm using here y prime. Okay, so we'll go ahead. Now we need to find y prime. So just to make sure that we don't have any algebraic errors, I'm going to distribute this negative. Okay, plus 3y squared, y prime equals 5. And here is step 2 where you want to, step 3 where you want to factor out your y prime, okay? So notice here how I have a y prime term here, okay, and I have a y prime term here. So everything else I'm going to move over to the other side. Okay, so subtract 3x squared, add 2y, okay, giving us negative 2x y prime plus 3y squared y prime is equal to 5 minus 3x squared plus 2y. Okay, and now I want to factor out the y prime. So we have y prime times negative 2x plus 3y squared is equal to 5 minus 3x squared plus 2y. And we're going to go ahead and divide to isolate our y prime. So y prime is equal to 5 minus 3x squared plus 2y. All over negative 2x plus 3y squared. Okay? All right. So it's important to note, right, that this is dy dx. That's what they wanted. They wanted us to find dy dx and then also evaluate at the point 1, 2. So now that I have this function, I'm just going to go ahead and I'm going to plug it into the equation. Okay? So dy dx, and then evaluated, so this is the symbol, evaluated at 1, 2 is equal to 5 minus 3 times 1 squared plus 2 times 2 all over negative 2 times 1 plus 3 times 2 squared. Okay, and there's your answer, right? You don't have to simplify. That is a numerical answer. So there it is. All right. Okay, so Notice how that one just had more terms, and especially we had to do some of the factoring and the reducing specifically in this section here, right? That was new for these types of problems. Okay, so number 4. Number 4 says, given x squared plus y squared equals 3, find y double prime in terms of y. So it's good to note, right, that they don't want just y prime, they want y double prime. So I'm going to have to differentiate implicitly. So we have 2x plus 2y times y prime is equal to 0. And I'm going to solve for y prime. So 2y, y prime is equal to negative 2x. And if I isolate y prime, we get negative 2x over 2y, reducing to negative x over y. Okay, so that is implicit differentiation. Okay, but they want y double prime. So I have to make sure that we have our y prime term isolated, which is here, right? So y prime is equal to negative x over y. And now I want to take the second derivative of this, okay? Now note, right, this is the quotient rule. This is the quotient rule. Okay, so we're going to have to go ahead and utilize that in order to take the second derivative. So y double prime is low d high, so low derivative of the top, okay, minus high d low, so negative x times the derivative of the bottom, which is a y prime, okay, all over the bottom squared, y squared, okay, and we can simplify here. So we have negative y plus x y prime over y squared, okay? And when you're taking the second derivative, what you're gonna have to do is we're going to have to substitute back in. So here is y prime. Well, isn't y prime equal to negative x over y? It sure is. Okay, so I'm gonna go ahead, plug in negative y plus x times negative x over y all over y squared. Okay, and for all intents and purposes, this would be your answer. However, we can simplify this, right? So I'm going to show you how to do this. So I'll bring it down again. So negative y plus, actually not plus, minus x squared over y all over y squared. Okay, in order to subtract, you have to have a common denominator. So what I'll do is I'll multiply top and bottom by y. Okay, and what we get is negative y squared minus x squared all over y cubed. Okay, good. All right, I got rid of the denominator, but they want us to write the problem in terms of y double prime in terms of y. So here's a little mathematical trick, right? If we look at our numerator, notice how they both have negatives. Well, I can factor this out, and I have x squared plus y squared. Okay, and now that I've done my math magic, I can go ahead and come back up here, and I want you to note x squared plus y squared, x squared plus y squared. Well, what is that? Well, in our original equation, x squared plus y squared is 3. So my final answer, y double prime, would be negative 3 over y cubed, right? And when they say they want the answer in terms of y, they only want y's, okay? So I have no other variables. All right, that is implicit differentiation. Here were some complicated examples for implicit differentiation. Hope you enjoyed it. All right, be easy, work hard. Catch you next time.